right. Hello and welcome to the 7th event in the series Future of Information Processing, with which we celebrate the 60th Jubilee of IFIP, the International Federation for Information Processing. My name is Elisabeth Schaumann and I'm part of the German Informatics Society. We are supporting IFIP in the Jubilee year. Today, the topic of our event is trends on computing systems, and I have the pleasure of briefly introducing to you your moderator, Graziano Pravadelli. Graziano Pravadelli holds a PhD in computer science, is an IEEE senior member and the chair of IFIP's working group 10.5, which works on the topic of design and engineering of electronic systems. Since 2018, Graziano is a full professor of information processing systems at the computer science department of the University of Verona in Italy. He's also been, or is the co-founder of EdaLab, an enterprise that develops embedded software and IoT-based solutions. His main interests focus on semi-formal verification of hardware-software embedded systems, as well as design and validation of virtual coaching systems to promote well-being and health of people through IoT technologies. I'm very happy to have you, Graziano. The floor is yours.
Thank you, Elizabeth, for the kind introduction. Welcome to all of you. Good morning, good afternoon, good evening, dependently on where you are now. It is a pleasure for me today to introduce very well-known speakers for this trends on computing system. The speakers are both from the academia and the industry, and they will give their view and perspective concerning new trends for low power and high performance computing system in the IoT era. But just before to start the panel, I'd like to introduce Professor Ricardo Reis from the University Federal of Porto Alegre in Brazil, that will introduce the memory of Professor François Anceau. The panel today is organized by the IFIP Working Group 10.5 on the design and engineering of electronic system. And Professor François Anceau was one of the members of the group. He recently passed away. He was a pioneer in microelectronic and computing system, and this panel is also in his honor. So please, Ricardo, if you want to say something about François and introducing also the workshop that we will launch the next January.
Thanks, Graziano. So this panel today is in celebration of the 60th anniversary of IFIP, but also is a tribute to Professor François Anceau. So François Anceau was a great pioneer in the design and automation of silicon processors and embedded computing systems. He was professor of the Enzimague Grenoble INP Engineering School in the first part of his academic career. He contributed to the creation of a Grenoble School on computer architecture in the 70s and early 80s, building a worldwide reputation that has endured until today. So we can say also that he was a pioneer in microelectronics in Europe. He's was responsible for the computer architecture group of the former Jan Koosmans Lab 7 until the early 80s. He was the founder of the SMP service, that is a multi-project ship service in 81. His group evolved as part of the Team 3 laboratory later in the 80s, and the next formed Team R laboratory in the early 90s. In the mid-80s, he joined Bull Enterprise in Clay-sur-Bois, where he led the pioneering industrial work on embedded computing system, doing the design of Bull microprocessor. Outstanding teacher and prolific researcher, he completed his academic career in the École Polytechnique in Paris from the 90s to the late of years 20. Extremely enthusiastic and passionate of his field, he collaborated with the KINAM in Paris until his very last days. But we are going to have a much more opportunity to know about the achievements of Professor François Anceau, attending a workshop that will be happen on January 10 in Grenoble, France. It will be a face-to-face and online event with the title Trends on Computing System Day as a tribute to François Anceau. And the event will include talks on the past, future, present of embedded system. These talks are given by international well-known personalities in the field, complemented with testimonials from François Anceau relatives, colleagues, and former students. So you are going to see a lot of the testimonials and presentations showing the achievements of François Anceau. So the program will be a full day. So in the morning, there will be some memorial talks with Monika Oblepska that was devised by Professor Anceau in years 80s. Also talk by Jan Homer. And in the morning, still in the morning, there is a talk by Giovanni De Micheli, also a talk by industry, and also a talk by Alain Guillot talking about the setting of the multi-project chip program. In the afternoon, some other testimonials and a talk by Frédéric Petrot from TIMA, then a talk by Koldum Torque about the 40 years of CMP, also a talk by Marc Duranton from CA. Then in the afternoon, I will do a talk. After me, Professor Manfred Glasser, that here today in the panel, also will do another talk. Then Subramanian, also another talk. Then some testimonials, conclusions, and then there will be a farewell cocktail and also a visit. So this will be a nice opportunity to meet a lot of people that have worked with François Anceau and that exchange a lot of research activities with him. And so soon you are going to see more details about the program. And I hope that all you will be able to attend the meeting in January 10th. So thank you and have a good panel.
Thank you, Ricardo. Thank you so much. And now it's time to start the panel. And so I'm going to introduce one by one the four panelists, and then they will guide us through the history of computing system from the past to the future, passing from great successes and also maybe some failures. The panelists are David Attenza, professor of electronic engineering and head of the Embedded System Laboratory at EPFL of Lausanne. His research focuses on system-level design methodologies for high-performance multiprocessor system on chip and low-power Internet of Things system, including new 2D, 3D thermal-aware design for many core servers, ultra-low-power edge AI architecture for wireless body sensor nodes, and smart embedded system. He is an IEEE Fellow and an ACM Distinguished Member. First, to present all the other, I give the line to David for his introductory statement, and then I will present also the rest of the panelists.
So should I?
You can share your screen, yeah.
Yep. Okay, because I didn't, sorry, my understanding was not very clear. You're going to present everybody and then.
No, just one by one to avoid 10 minutes of presentation. And so in this case,
okay, so let me just share the slides. Share the screen. So I should be able to see now.
Yeah, perfect.
Let me remove the screen. Okay, so then, so welcome everybody. Thank you, Graziano, for the kind introduction, and thank you, IFIP, for the invitation to be here. So I really appreciate the opportunity to honor this very interesting discussion and see what we can actually try to think of how we can make the computing architecture as efficient as our brain, which was the initial theme that we have actually been asked to comment. So my view is that, first of all, clearly we are not as efficient as computing-wise with our current electronics as what you have basically as our bioengineering machines, which are basically the brain. So if we think about it, we can see that we are like 3 orders of magnitude worse than what we actually are today. And the reason for that is the way that operates is very different. So if we think about it, you can see a clear image of the brain that you see on the left. And there you see that there are fundamental differences. First on the structure, because it's a 3-dimensional structure that we don't have today in most of the electronic systems, where it's extremely high dense. But even if it's high dense, you actually see that, as you can see on the image, in the animation, there's a lot of stimuli that comes in, but only very few times the actual system really reacts. So it's a very, very specific set of operations. So even though you have very high density, you limit the power consumption and the effectiveness to the maximum by having really reactions only when they are really needed. So for me, this is something that we don't have today. So the fundamental issues that we have is, or missing, is that we want to make sure that we don't waste energy. So we want to self-adapt utilization to demand. We want to closely link memory and logic. And we want to make sure that we integrate power and cooling. So these are fundamental technologies that we haven't really developed in our systems. We are more or less targeting each of them. I think we have to change all of this to do all these things seamlessly. One of the clear examples of technologies that we're trying to do that and were for a long time not working correctly was 3D integration. So the first thing we had to do, why don't we make the processors and computers 3-dimensional? And we saw there was a huge problem that was about power density and cooling. So the idea here is that can we do something else in that direction? And I would like to present one of the projects that we have been working on at the PFF, which actually is pretty strong, that goes a little bit in that direction to try to motivate the things that I think we need to do in a disruptive way to change that. And this is part of an ERC that I was leading. So first thing, what do we have to do to change this? I think there are 3 things. First, we need to really make sure that we can combine power and cooling. So that's what I call, we need to create some electronic blood for doing this thing properly. And this we need to make sure that we can actually have one single medium for doing all these things. So we may go from power delivery through electric wires and efficient cooling through liquid, which is currently done today, to something, a unique medium, somehow, which is very much not just electronic, but really going beyond multidisciplinary capacity to really do something that is kind of on-chip microchannels with integrated cooling and power delivery. In that case, we can cool down very effectively the system. And on top of that, the reaction that happens in these channels because of the heat can be absorbed by these fuel cell arrays to actually make sure that we recover part of the heat. If we do that, we can actually make a system much more energy efficient, but particularly not overheating, which is a problem that we have had for many years. Now, if we bring the 2 pending parts, we have to make the system much more closely linked memory and logic storage. So in the brain, we have the cells, the neurons that actually store everything and actually compute at the same time. So we have to avoid what we do today of having this separation between logic and memory. And I think it's something that will go on. So to do that, that can bring us another 10 times energy efficiency, 1 order of magnitude efficiency, if we do it really well done. And finally, the last thing we are missing in current architectures is really the part of specialization. So right now we have big cores, small cores, and things like that, but we don't really have something very heterogeneous that is really dynamically able to adapt as the brain does. So I think if we're able to do that, not just having big and small cores, but really fully adaptive with a plethora of things all together, we can actually have this whole thing that will adapt dynamically to the execution of different applications. So if we try to do all these things together, and here is just a mock-up of what I think was missing. Here I show you a first mock-up that we did with the people from IBM in Zurich, where we show this fancy 3-dimensional chip, which is a cube, trying to create these things. And I'm still not mixing here the part of new technologies, which I think are missing. Then you can get a system that really operates a very low and a very balanced temperature of 52 degrees all the time. Will make the system work pretty uniform without problems of overheating on 3D. We'll recover 30% of the energy back so far, and we'll actually make the system much more credible with respect to what the brain really is. And I think we have to really address these 3 main issues to really go further and actually make the system work effectively. That's all I have from my part.
Thank you, David. So first to moving to question, I'd like also to introduce all the other speakers. And the next one is Professor Nikhil Dutt. He is Counselor Professor of Computer Science at the University of California, Irvine. He is an IEEE Fellow as well, and an ACM Distinguished Scientist, ACM Fellow. And his research interests are mainly in embedded system, electronic design automation, computer architecture, optimizing compiler, system specification technique, distributed system, formal method. And in all these fields, he received several awards, and he was keynote speaker for many conferences. So please, Nikki, what you respond to the idea of David?
Thank you, David, for that really nice perspective. Are we going to do Q&A first and then presentations, or should I go with my presentation?
As you prefer. You can go with your presentation.
I'll go with the presentation, because then I think it'll be easier then. So actually, thank you again to David for that wonderful presentation, because it's a nice segue to my presentation here, where I'd like to pop the stack a little bit and try and address this issue of this phrase people use called cognitive intelligence.
We cannot see your slides, Nikki.
You can't see my slides.
No.
Okay. All right. It's swap display.
You're not sharing.
I think you're not sharing yet.
Oh, I'm not sharing yet.
No.
Oh. Okay. Hold on. Sometimes you test and it doesn't work. Okay. There we go. Let's do that again. So again, recast my presentation from the perspective of what can we do to discuss these issues of cognitive intelligence. And so let's think about what that means. And to do that,
not yet, Nikki. Sorry for interrupting you, but we still not see your slides.
Clearly, I'm cognitively challenged.
Now you are sharing all the screens, so probably.
Let's see now.
Okay.
And I need to flip.
Perfect. Thank you.
Are you seeing my display, or are you
Absolutely.
seeing...
Now we are seeing the presentation.
Okay. So the discussion was really about cognitive intelligence in a computational context. And so what I want to set the context is, let's go back to biology for a minute. And if you look and think about what we mean by cognition in living beings, and look at how it's evolved over time, you can start with very primitive species like worms, which have very small nervous systems, and you might call them brains, going all the way to what we think of are very evolved human brains. And of course, you can look at the number of neurons and synapses, and these grow by orders of magnitude. But what's really important, I think, from the perspective of computing is, what kinds of cognitive functions do these creatures exhibit? And what can we take away when we build new computational platforms? I think that's a very important perspective we need to think about. So, and then related to that is, how can we do that efficiently? So if you look very closely at these primitive creatures like worms, they have a central nervous system, and they typically respond to stimuli like light and smell. If you go up in the evolutionary chain, you might go to something like a fruit fly, which can do, navigate in 3D space. There's an ability to find food and perhaps even form groups. If you move up to something like a honeybee, it does more than the fruit fly, in that it also has more comprehensive group behavior, but it also has this ability to self-protect. And we know that if you've been stung by a bee. And it also has this notion of short-term memory, where it can actually find certain things. Moving up in the chain, you can go to a mouse or a rat. And there we have the ability to do spatial navigation, where the organism can learn routes and landmarks, and it can also replay routes. And this is very important, the idea that it can store memories in the hippocampus and then be able to replay that, which is this idea of not only learning, but storing past memories and replaying that. If you move up again to something like a cat or even a dog, you have the notion of physical balance. They exhibit primitive emotions, and they also have longer term memories. And of course, if you move up to humans, we have very developed cortexes. And so this is the new brain, which allows us to do higher level reasoning, planning, and also exhibit self-awareness. So, if you're thinking about how do we actually capture these concepts and platforms and where are we today, I would postulate that today what we have is the idea that we have systems that are typically more reactive or reflexive. And this is the fast system that we think of in our bodies, which is the autonomous nervous system, versus the other part of our system, which is reflective and slow, which is using introspection, which considers both past and future outcomes to do planning, strategies, and policies. And humans, for example, use these two systems opportunistically to do this in a manner that allows us to respond to stimuli and operate in the real world. So what about our current state of computational platforms? I would posit that today we have systems that are primarily reactive and reflexive. We tend to do in IoT systems or platforms, we can monitor the system state, and through a control loop, we can adapt and then change our system behavior. So for example, if you notice in a chip that a certain part of the chip is getting overheated, we may do a simple adaptation that allows us to migrate that task or switch off a core, etc. But I would argue that what we want our newer platforms to do is to have the reflective and introspective aspects of planning. And what that means is that we want to be able to build self-models of the system and be able to do proactive adaptation. So you can think about the past and also the future to do more effective management of resources and build more cognitive architectures. So let me just finish with an outlook. So I think that there's a great opportunity to rethink what we mean by cognitive intelligence in a computational context. And so I call that computational cognitive intelligence. This has many, many parts, and I won't list all, but I'll just say a few here. So we must encapsulate this notion of learning. How can we capture new policies and situations and incorporate them moving forward? How can a system do that? And this requires seamless integration of both the hardware platforms and the software platforms. We need to be able to incorporate self-X and situation awareness properties. We have heard these terms before. You know, there's a whole plethora of self-X properties like self-adaptive, where you can change the policies dynamically, or self-healing, where you can become resilient to failures and anomalies. Self-optimizing, as the context changes, you can do resource management adaptively. Self-harvesting, how can you use energy resources very effectively and opportunistically, looking at where you can get energy from, and how can you utilize both context and situational awareness. So I want to end my position statement by saying that, you know, we've heard the phrase AI as artificial intelligence. I would argue that what we really need is augmented intelligence, which is using all of these properties to try and better manage our resources in a coordinated manner. Thank you.
Thank you, Nikhil. So we have already a lot of material for the discussion, but we have also two other panelists, and the next one will be Professor Manfred Glessner. He is IEEE Fellow, head of the Microelectronic System Research Group at the Technical University of Darmstadt. And his research activities are in the areas of embedded system design, high-level synthesis, physical design, especially for intelligent signal processing, mechatronic, and smart system in general. He was, in 1982, the first in Germany to design with students a multi-project chip as part of the regular education. And he also recently got the Silver Core Medal from IFIP for his significant professional achievement in the area of microelectronic system design. So please, Manfred.
Okay, Graziano, can you open my transparencies?
I don't have your transparencies. Probably, I don't know if Elizabeth has them.
You need only give us permission.
Yeah. Nikhil, you have to stop your sharing.
Elizabeth, can you stop my sharing for me? Thank you. I had trouble finding my
Probably Elizabeth can do this because I have no control on this aspect.
I think the transparencies of nickel have to be closed in the first instance.
Elizabeth, are you online? Because we have to stop the presentation by Professor Dutt.
Actually, I stopped sharing at this point, so I don't know why it's still showing.
We still see your presentation. Ricardo, you cannot stop, right?
No, but I think if you try to share, it closes the other one.
No, because I tried to share myself, but it says that it is impossible till the current user.
We got the same answer.
Okay, we have a problem here. Okay, now Elizabeth.
It looks better now.
Okay, thanks.
Now it should work. Sorry.
Thanks, Elizabeth. Now, Manfred, you can share your screen.
Ah, yeah, now we have it. Okay.
Perfect. Okay.
Okay, thank you all very much for the kind invitation in the last minute. I'm not an active professor, so I'm in the beautiful situation to be a professor emeritus, and this means one has much more degrees of freedom. Somebody has to take care of the kids.
Yeah, Ricardo, can you stop? Can you mute your micro, please?
It looks better now. Okay. This is a picture from 1963. I'm not stepping into hard research topics immediately. At that time, I was a second-year student in physics and mathematics. And in that time in Saarbrücken, near the French border, we had just 3 computers. One in the university, a classical SUSE computer, where the Germans are very proud on it, and the banking people, they had a computer, and a third one was in a elektronisches Rechenbüro. They are from civil engineering, and they built big bridges, and they were the first one to use such computers, and I was earning my money for studying at that place. The people, the historical people in Darmstadt, they are proud on a computer with the name DERA, Darmstädter Elektronische Rechenmaschine, from Professor Walter. It was a real operating system. It was built at the beginning of the 60s. It was an electronic valve computer, and other universities, like when you remember Piloty, Robert Piloty, his father was president of Technical University in Munich, and they built their own computer in Munich, the PERM, Programmable Electronical Rechenmaschine in Munich. So when we look to from the beginnings in the 60s, when we had the change from valves to transistors, we have experience, and we can be lucky to have that we were working in that period, that the electronics area had a big change, and there was a big driving force behind the technological, scientific, economical progress in the last 50 years. I don't want to go to the figures here, but we see that there is really a big world market, and the European share is in principle much too slow to be of real important value. But when you see the growth rate here of the electronics industry with 8% per year, that is an excellent value. So at the beginning we had this period with the electronic vacuum tube computers. Then the transistorized computers came up in the second part of the 80s, and they were replaced later on by integrated circuits. And then we came up to the VLSI times, with very large scale integrated circuits, and that was a starting point for many colleagues here which are participating in the presentation today. We have the here on semi-logarithmic scale the chip complexity, which is an incredible curve for all the years here, and we saw what we got by our colleague from Lausanne, the 3D integration of modern processing systems, and it was clear that from the beginning of the year 2000 the technology was able to integrate more cores on a chip, and we see here that people are going up to many core systems here, experimental circuits, and of course limiting finally also the interconnection and the processing. In 1981 there was an important change in our industry, because on one side we had the technology area, on the other side we had the design area, and the circuit complexity with integrated circuits was at the beginning so small that the physics people from the technology development groups, they also designed the circuits, and it was the achievements of Lynn Conway and Carver Mead to introduce a formal logical separation between both areas by introducing design kits, and that was an important step. And the technology people in Germany, at least, they didn't like this step at all, that this beautiful design area was taken out of their hands. But it is working, and it's an efficient model of industry cooperation which we are using nowadays. We are talking about high tech here, but when you look to the TV news, what is going on in the world, you see that we have really an enormous amount of problems. Here are mentioned the 10 important problems. It's from a publication from Philips. I got it from IMEC. And you see here the 3 points that are dominant, probably, that we have enough energy. It's a big topic, water, food, and so on. And we have really to cope also with these problems nowadays. This is a photo from the first multi-chip wafer at our university, where we had an MPC here with individual student projects. The company Bosch was helping us with their e-beam writing of the mask information. And when you look nowadays to a newspaper, everybody is discussing the chip shortage we have. They can give you reasons why we have this chip shortage, but it's an enormous problem in especially the automotive industry, also the other associated industry here, and it will have an enormous negative influence on the fabrication of products like cars, equipment from TV sets, and so on. So, in addition to that, we were perhaps at the beginning focusing on processors by themselves, on the architecture of processors by themselves. Nowadays, we go to the sector that we have more than more subjects, including sensors, actors, machine learning topics here, and we see a certain form of democratization of microelectronics in the form that we have now devices like this Arduino device that is giving access to the integrated circuit technology to a broad range of people, starting with 3 euro chips, starting with 3 euros for such an Arduino board. And many people can do excellent work in control applications using such components like the Arduino. And probably the Arduino is the only component that has the name origin from King, the Italian King Arduino, and in the bar Arduino, these people around Massim Banzo, they invited this area. Also Massimo Banzi has the advantage that he started the so-called maker movement. Maker movement means that in Italy it's now practice, standard practice, to invite in December young people, researchers, anybody who has something interesting to present on the level of integrated circuit applications. And this is a so-called maker movement, and that is really a form that we distribute electronics, microelectronics to the society. And it should not be underestimated, the value. And now we have also the Fab Labs in universities. In many universities I saw such Fab Labs working quite well under the direction of graduate students. So that is an example of the Maker Fair in Rome. Everybody is coming there, and the people are from different areas here, and they are using the microelectronics for improving their products. This strategy has been extended to open science hardware in general, so more physical areas or more areas from biology, pharmaceutics, they are now also involved in this business and try to get profit of it. And there is a global open science hardware community in our field here, and they have their own conferences. They don't understand too much about using complex CAD for microelectronics, and there would really be a good idea to help them to get accepted and get in knowledge with the modern devices we have. When you are outside in the world and you are waiting in the line in the supermarket, everybody has his smartphone to talk, to read something, and I can recommend you the books and the publications of Sherry Turkle. The famous one is here, Alone Together, that people are finally in a lonely state, but they all work on these handies, smartphones. So I have to look a little bit on the timing. This Open Science Hardware Group, the abbreviation here, Gathering for Open Science Hardware, this GOSH community, they are running their own conferences. They are not restricted to high-tech areas, but they try to go to many places in the world, and they have interesting applications. For example, some are mentioned here, digital biology laboratories, the PCR method, for example, to copy DNA molecules, what got very important now for inventing the new drugs for corona disease. And we see here applications in open source magnetic resonance imaging. So it's very interesting what is going on in this field. What, in my opinion, is a big problem, that is how we get interested students to our area. I was recently in Tallinn, and in Tallinn they had 14,000 students at TTU. Now they are on a level of 10,000 students. We see it in our university also, that the technical engineering areas are not the dominant areas that are sought by the young people here. And I have here quite interesting foresights of the global engineer by Ratehi, and we have here figures that 8 billion of the 9 billion people on Earth in 2050, they live in developing countries, and the economic growth is despite only 2% below the expected economic growth in the other areas. So what I said with the social problems, with poverty, is still acting here. And another interesting topic is that we all speak English nowadays, and the headquarters of big companies will probably move typically out of United States and will go to other countries here. As a student, I bought in 1985. We had, and François Anceau was also there in UK, a conference, and many people from Japan were there, and they were talking about their 5th generation computer systems. Everybody was amazed and said when they get this working, they have reinvented the world and this area here. As I see, somebody like Feigenbaum wrote this booklet on the 5th generation computer, but from the many diagrams, architectural features they presented on the conference, we never saw a working 5th generation computer. And when I see the big money that is flowing now to computer science faculties working on the topic of neural network, machine learning. By the way, the people who designed the DERA computer in Darmstadt at the beginning, they also had ideas about machine learning. So this is a topic that what is at least 40 years old. And I doubt if they will really get the expected profit, and that is an important message, that many things in our area depend on the availability of modern semiconductor technologies. We are coming to a limit according to Moore's law and the resolution limits. We will look to other technologies, but no technology is now available that has that it is by industry standards, that it can be used for new devices, and that is a big area. And this democratization of microelectronics, that everybody can use it. Bosch opened a new fab in Dresden. They produce chips with 100 nanometer technology, because there are chips that are really speedy enough, are working excellent for the applications in automotive electronics. So we will see another excellent time, and we can only hope that we get good students, smart students working with us. In my group I had always about half of them coming from different countries. You know, Leandro Intrusiak, for example, about 15 of the people are professors themselves, and I hope in the future we can look to also such beautiful developments, as we had the luck to be a member of that community. Thank you very much.
Thank you, Manfred, for your historical perspective also.
Yeah.
And then we have Victor Greenblatt from Synopsys. He's currently the R&D Group Director and General Manager of Synopsys in Chile. He has a PhD on IoT for smart agriculture, at the University of Bordeaux. And he has expertise and knowledge in business and technology, and understands very well the trends of the electronic industry. Therefore, he is often consulted for new technological business development, especially in the IoT, EDA, and embedded system. So, Victor, please give your industrial view.
Okay, so thank you very much for that. Thanks for the invitation. Thanks for the presentation. I hope you are seeing my screen now. Okay, yes, so what I'm going to talk a little, and it was very interesting what Professor Mandel say about the history of that. But I'm going to talk a little about the computing trends and EDA challenge. And I put E.DA because we have to move from electronic design automation to design automation. And it was very interesting also what the other panelists said. So let me start with that. So what are the computing trends today? And after we are going to go into the EDA trends. So the high performance computer, as we know, the TPU pods and the quantum computing with the Josephson junction. And of course, the biggest challenge in building that is the integration of CMOS electronic and superconducting qubits to the same board and chip. The cryogenic CMOS is also another technology that's coming out. The CMOS compatible qubit, the silicon photonics, and the photons instead of electrons. So we have a lot of new technologies, and we should ask ourselves, is EDA working on that? So let me start giving a small view of EDA over the history, because, you know, at the beginning, we start using this Calme station. For the people that are a little old, they will remember that, the Calme station, to do all the layers of the and the mask. And after we moved to the automatic place and route tools, where we were having the layout done automatically. And in the 80s, we start talking about synthesis, about logic synthesis. And I remember very well that time where we were trying to do some kind of synthesis, some kind of Boolean optimization. And after we moved to the synthesis, and synopsis appeared in 1986 with the design compiler tool. And after we moved to some other tools, and today we have a complete set of tools that allow us to do chip design in the analog and digital side. But what is going to happen in the future? So let's start working on that. So the first thing is to, the design automation, and I'm changing my words to not talk anymore about electronic design automation, must be extended to deal with quantum computing and its enabling technology. So, for example, we need layout tools to handle curvilinear objects, such as Josephson junction. An equation on the photonic, we use equations supporting silicon photonic, new data representation. We need computationally efficient RLC extractions. Today we're working with RC extraction. We know very well how to do that. But when we're going to move to the quantum computing and so on, we need to work with inductors. So we need to do an RLC extraction. We need logic synthesis to handle quantum gates, superconducting electronic gates, optical gates, and not necessarily in this order, adiabatic logic and reversible logic. So there is a lot of new things that we need to start handling that. We need place and route to handle fan-out equal 1 and initially limited routing resources. So for example, let me give you an example on Josephson junction versus transistor. Not all gates are equal. If we take a NOR gate, a normal NOR gate that we know very well, it uses just 4 transistors, 2 NMOS, 2 PMOS, and this is the image we can see there on the top of the screen, top left of the screen, we have a NOR gate. The same one in Josephson junction will use 12 Josephson junction devices. So, and this is what we can do, we can see in the bottom. So we see that a NOR gate that is smaller and the normal CMOS will be bigger in the Josephson junction. And a D flip-flop, it's the opposite. It's 6 NMOS and 6 PMOS transistors in the CMOS technology versus 4 JJ, Josephson junction, in the Josephson junction function. So you see the image there. The flip-flop is on the right. The NOR is on the left. So for example, we start thinking on optimizing area. So we will have to be very careful. And the inverter is the biggest function, and the biggest area, the biggest cell in the Josephson junction function. So we need to start also talking about design automation for superconductor electronics. So what remains the same and what changed? Universal gates, transistor and JJ lead to a very different result. So we cannot just design in the same way. We cannot just seek in the same way. We have to change schematic, layout, RLC extraction, PDKs. So we need a lot of new PDKs to be able to do this kind of work. RLC network reduction. L extraction with high accuracy is critical. Circuit simulation, how to model the characterization. And for example, if you consider, and we will see later, quantum computing, and you want to go to sub-Kelvin temperatures, and you want to move the CMOS to the 4 Kelvin environment, you will have to extract everything and to do all the models again and to characterize them on temperatures. And we were not taking care of the temperature in the past. We just started to talk about temperature with the automotive. Functional verification, sign on the surface, different phenomena, the flux swapping and so on. And now we can see that what else? Logic synthesis and place and route, splitter versus buffer, new clocking scheme, the power, the bias delivery, the current recycle, use of PTL and JTL with the exact matching delay between paths and so on. Area is king. The area, because you know, in superconducting electronics, the power and the speed is so much better than CMOS that area is the problem. How we reduce the area. We can have with some quantum computing or some Joseph junction or superconducting electronic application, the area will be a factor of 10 maybe, more than CMOS, normal CMOS. Physical verification, we don't have Manhattan geometry, static timing analysis, so it will depend on exact arrival time, detect the presence or absence of pulse following a clock pulse and multi-pulse error issue. So this is the thing that we need to take care of that. And design automation for quantum computing, what remains the same and what changes? Well, again, so we have the adiabatic quantum flow parameter, logic family in adiabatic switching model for reversible computing, which is not the case in normal CMOS. We don't have reversible computing, and this is that's a candidate for quantum computing. Gate libraries, we see here a lot of different things about the gate libraries. They are different from what we have in CMOS. Circuit simulation, we have to go from Monte Carlo. Functional verification. An n-qubit quantum computer is 2 to the power of n more complex than an n-bit classical one. So maybe we will need to use a quantum computing to simulate a qubit quantum computer because the complexity is too big. Logic synthesis and place and route, reversible logic, I already told the number of output is equal to the number of inputs, no copy, fan-out restriction, no erase theorem, the time sequence versus space. When we will talk about quantum computing, we'll talk about sequence. In CMOS, we talk about space, layout, error correction, amplitude and phase alignment, and so on. Physical verification depends on the underlying device technology, trap-ion, superconducting, quantum dot, etc., etc., etc. And design automation for silicon photonics. The first change is the modeling and simulation. We need to model again. We need to do better simulation. Mix optoelectronics and or electro-optical simulation. Multiphysics, thermal, RF, layout equation, layout. We have to work with equation now. We don't have any more polygons. The place and route, we have curvilinear stuff, parasitic extraction, design rules, check and layout versus schematic. What is the meaning of that on silicon photonics? Variability, logic synthesis, linear algebra versus truth tables. We are going to work now with linear algebra and functional verification, test IP and parametric and program. So we are going into a new world that we are working on getting the tools for that kind of thing. And of course, they will be needed to go into production for the different new processors we are going to build. Thank you very much.
Thank you, Victor. So all of you said several interesting aspects moving from the more application level field till the very low level aspect of the design automation. You talk about augmented intelligence, about electronic blood, about quantum computing, and so on and so forth. And so my first question is, what do you think could be the most breakthrough technology to make the difference in this new computing era? What about the technology that can really enable what you foresaw during your initial presentation? Please, David.
Yes, so I would say, I think there are a few answers to this question. So one is, and we have seen quite a number of technologies exposed, so I don't think there is a single one. I think one of the key aspects that we need to go for these future architectures is first, not to be strictly limited to one technology. So clearly there is no silicon that is going to be the dominant and so on what has happened. I think technology-wise is the more mature one, but you have seen that there are a number of things that can happen and I think goes in the direction of systems, that we need to look at how it's done, goes back to the presentation of Nick, how it's actually done for a good perception understanding, how it can be done in software or other technologies that actually enable that. And the same thing happens in what I presented, for example, is the idea that you need to go beyond this idea of being stuck to electrical wires and do the things there, because these are not giving you the optimality that you need. So I think we're going to see a multidisciplinary development. Personally, I believe quite a few of these nanotechnologies that actually enable both storage and computation together, to actually enable this concept of in-memory computing and stuff like that, are going to be key. And I think the part of the solving the problem of cooling plus providing supply power to make it really energy efficient is another story.
Thank you, David. Any other idea, Victor?
Yes, I fully agree with David. And one of the things I want to say is that there is this quantum computing could be very important for some kind of application. We don't have to think that quantum computing will be for everything. Because, for example, working in agriculture, we don't need quantum computing so far to look the behavior of crops. But if you want to do a catalog of proteins, maybe you will need some quantum computing. And what is interesting is that the two ways that we are doing that. One is that we need to cool the CMOS electronic that is working with the qubit, and on the other way is to try to move the qubits out of the cryostat. So there is an interesting research, and I think this is a key topic, how we make a real quantum computer that I can put on my desk. So how we work on that. And there is very interesting thing at EPFL, at Australia, people are working on that as well. And also in China, they're working more with photonics. Other guys are working more with cooling down CMOS. But I also think this is a good trend that we have to be considered.
If I can add to that, Graziano, I think David made an interesting observation, I think very important. So if you look at the diversity of applications and the kinds of applications, they're going to demand very different needs from the sense perspective of how do you sense the physical world? What kind of data are you storing and computing with? How do you actuate? And how do you actually interact with the outside world? So each of these, if you look at that entire pipeline, if you will, they're going to be a variety of technologies that are most suited for each of those. So you might see, for example, in vision sensing, now we're seeing neuromorphic architectures that are very interesting. Now they could be implemented using technologies that do memory and storage in memory and computation together. If you're looking at crypto, perhaps we're looking at a different scheme. If you're looking at high performance computing, is different. So I think very much the case that we want to be looking at not just heterogeneous processors, but heterogeneous technologies.
Yeah, thank you. I see that there is also a question from Salvador. So please, Salvador.
Yeah, hello all of you. Thanks a lot for all your insights. Sorry, I joined a little bit late because I had trouble with the firewall at work, so I had to go through the iPhone. So I have an image which is not also very, very high quality. So I see some links between what you say, some of you, with respect to trends on computing, especially high performance computing and quantum computing and cryogenics, because people today, they are talking about the possibility even for high performance computing to cool down to cryogenic temperatures, but not for quantum, just down to around 77 or 80 Kelvin, because this would allow to use liquid nitrogen rather than helium that is rare in nature. And this would allow to cool down with the right cryo reactors as much down to 80 Kelvin, all these high performance computers and other applications. And then apparently you may have an energy balance where you have less losses of energy, and it might be much more efficient than doing it as it is done today at normal room temperatures. So what is your take about these large programs on cryogenics trying to build you know, these new computing platforms back down to 80 Kelvin?
Very specific question. I'm not a computer engineer, I'm a computer scientist, and so it would be very difficult to me to answer for such a kind of question, but I'm interested in understanding if some of you can answer to Salvador.
Yeah, I think there are 2 points here to discuss. So one is when we are looking at what are the capabilities of what we can do. Another thing is what is really realistically sustainable from the perspective of what is actually doable. So indeed, this type of approaches actually go really beyond very often what we can do as an exploratory thing to really see if it can work out in a more efficient way or not. The problem here, to be honestly, that they haven't really, and it will be taking a while before they can really prove they can be sustainable in the sense of the effort of cooling down the system to these technologies is enormous with respect to actually what you get as a benefit, real factual benefit with respect to current computing systems. So I think this is a very interesting exercise, and I think it goes in the direction of what you would like to have to say the trade-offs, but honestly, I don't think it's really the way that should be going. In the sense, in the final run, what you should be able to find is ways to create quantum computing and these other approaches that actually are a much more reasonable temperature that we can afford, or maybe then we have to send it, I don't know, somewhere outside the planet to be able to actually do that, to actually do it, because the overhead that you have is so high that on practical terms, it's not really something useful. But as an exercise, I find it perfectly reasonable and justified because we are trying to see what will be the potential trade-off or benefits that you have. And we have, in fact, a couple of exercises like that on quantum computing led by Eduardo Charbon, also at EPFL, and go in the same direction, although conceptually the overhead that you have for this, for showing as a final long-term benefit is not really justified for the moment. That goes in the direction of finding, like what Nick said, finding different technologies, how it can be used on different particular use cases that can make sense. I think as a general purpose doesn't make any sense.
Any other of you want to add something about this?
I would like to agree with David and Nikki that it's based on the application. We cannot consider that we are going to put quantum computing or cryogenic on all applications. So it is very important. I have seen also that Australia, there is a company in Australia that made a little box, and they say you can have your quantum computing at your desk and you connect it to your computer. But we have to see what is going to happen. But maybe 10% of application will need that, and 90% will need the rest. I'm not going to use an Excel spreadsheet on quantum computing. So it is very encouraging that we are doing things, but it is for some very, very, very specific applications.
Okay. I would like to provoke you with a different question now. If you look at the history, computer science born very, very early with respect to computing system. Okay, we can say that computing system started with some calculators in the middle of the 16th century probably, and then later on only in the 19th century it got again some visibility, while problem solving and the idea of programming is much more radicated in the history. Okay, so do you think that in the future the role of computing system, in the sense the hardware part, will be more important than the software part, or the software will be much more important than the hardware components? To achieve the result that you discussed during your initial statement, for example, augmented intelligence seem much more on the software side with respect to the hardware. while electronic blood probably is much more on the other side. What do you think about this?
Maybe I can lead off just to, I think it would be wrong to try and make a distinction between hardware and software. I think we really need a tight coupling based on the kinds of applications that we're looking at. And there, because of the needs of the applications, it may be that there's a very little small thin software stack where everything's done with sensors and with maybe new computing technologies for certain applications. On the other hand, there may be others where the software stack is so important to be able to deliver the quality of results for the learning or whatever you're doing. And there you might need the dedicated hardware. And so there's a mix. So I think it's a very hard question to answer, because it very much depends on the kinds of applications we're looking at and what we want from that particular application. Is it the case that you want to have a very high fidelity result in a dynamically changing application scenario? Do you know a lot about the application where you can optimize that and sort of customize that in hardware? So I think it's a very open question, in my opinion.
If I can add something to that, I will say that today we are working a lot on tools for what we call the software hardware co-design. And we have, so the way that we design a system, we're not talking anymore about the chip, we talk about designing a system, an IoT system, automotive system, is to put the different part of that system and to start looking and simulating the hardware and the software at the same time. So you can move very easily from one side to the other based on your requirements. If you need a very, very fast system, maybe you will have to do some part in hardware because they will be faster, even in analog hardware. But if you need something that, I don't know, that have to have a lot of calculation process, maybe you will do that part in software. But with the tools we have today, that this co-design is much easier and you can move from one to other during simulation.
Okay, thank you. I see Manfred with your hand raised.
Okay. Concerning these MPCs, for example, I saw recently that the IMEC people are offering a new type of design together with gallium nitride. So this area of gallium nitride seems to be very important in the first instance for power electronics applications, but on the other side it seems that such technologies, and Victor might know it better, such technologies can also be used to replace to a certain amount silicon, and that would be a direct step forward into new technologies and new applications. For me, the question is, of course, it would be nice to have this photonics applications, but what is the real the winning situation that we have the photonics applications? When we got the transistor technology, it was clear that they had to replace electronic valves concerning power consumption, space and everything like that, speed. But what do we gain in using, for example, these complicated technologies that you were mentioning?
Okay.
If I can add something based on what Manfred was saying, it is important to know that maybe 5-10 years ago, we were having hardware was more a commodity and everything was done in software. So we had a lot of processor and CPUs, GPUs, and that's it. So we were putting software. Today, with the specific application we have with the artificial intelligence, machine learning, we are doing more and more our own hardware because it's based on the application. So this is the big change I am seeing right now on what is happening in the silicon part. So we have more and more companies designing their own chip. We can see now that companies like Facebook, like Google, like Microsoft are doing their own chips. That was not something that you will think 5 years ago, but Facebook, Apple, Google, they all have their hardware department.
Maybe what I can add simply as a continuation, I think, and that goes back to what actually Victor said about Facebook, Microsoft, and so on, because I see that many of these companies, they have the potential to actually optimize much more for the type of software stack that they have as well. So it goes back to what actually Nick said. It's very difficult to say that hardware is more important than software. I don't think so. I think you need to see much more this idea of co-design of architectures, because even if you take gallium nitride, which actually we have here, Professor Mattioli at TPFA, which is one of the leaders here, we're discussing with him very recently about EDA tools for gallium nitride and what type of technologies they have. There's nothing. So actually they custom do designs and they really have to optimize by hand every single chip. You have billions of chips that you have to build. It's not going to fly. So actually you need to have good understanding of what is the target platform you want to have on what is the software that's going to be running, and based on that, try to use many of these new technologies. So essentially, I think it's really a co-design problem even more than before, because right now you have not just silicon, but you have many other technologies that can be working well for different areas, and these big players that can have the potential to actually tell you the whole stack and how they want to design and design their own chips. But going back, you need to understand a good knowledge, and I would be very hesitant to really put their hand on saying hardware or software is more important. I think both need to be go together, which is what happens if you think about how cognitive understanding and the architecture of the brain is. When I'm going back to my presentation, it's all very heavily interconnected with each other. So seeing how often you need to access memory, that's why memory is stored at the same time as computing is performed, and what type of operations are done are relatively dependent on the type of software, which in this case, application that you run on the brain. So I think that both are equally important.
Okay, thank you.
Can I answer?
Yes.
Or make my comment? I have observed that the big players, they all go for their own processor design, but I guess that is not for technical improvement of the architecture or so. It's simply an economic response that they feel better when they have their own fabrication in their own hands. But on the long term, we have to see if this is really working, because there were companies like ARM, and ARM was serving many, even Samsung mobile phones get their processors with design from ARM, and they stopped a certain amount to do their own development. So it's funny to see, and it's also funny to see that the solid-state circuit people, they are now also involved in open source hardware activities, and they run their own workshops, and these workshops are quite interesting, and they are certainly a mechanism for us to go on with the silicon world. My question was not answered. What do I profit from using silicon photonics?
Okay, I think that we have just a couple of minutes before closing, and I would like to ask you a final question. You talk about, as said, augmented intelligence, electronic blood, quantum computing, and different kind of architecture or computational system. And probably the future application can have some ethical challenges to be addressed. What do you think the most ethical challenge to be addressed can be in the near future?
Perhaps Victor can answer this question, because you told us that you are working with applications in agriculture. This is certainly an area where many people can profit in the world, and I have seen other institutions in Estonia, for example, who have that topic in mind.
Yeah, it is interesting to see what we can do in applications like agriculture, where we have to consider food, we have to consider how to feed the population and so on. And the ethics are very important in this part. And one of my major advice on these kind of things is that we, electronic or computer science people, we don't know everything, and we have to work with the real expert on those topics, because if not, we are going to do things that are not correct. On the other hand, just applying technology without looking at the consequences of what we are doing will also have a big impact on that. And for example, one of the things I know that is regarding emissions, the greenhouse emissions, agriculture is responsible for 1/3 of them. So do we want to increase productivity, continue affecting the planet resources? Do we want to continue doing agriculture the same way? No, we have to change. And this is where we have to apply technology, how we change, how we increase the productivity while keeping the planet safe.
Yeah. That's a good answer.
And I can add to that also. I think, you know, there are many dimensions of ethics. If you look at ethics from the perspective of individuals, from the perspective of local societies, from the perspective of global scale, what the impact might be. And we've seen technology has already changed how people behave, how they interact, how they or don't interact physically. And I think you know, there are large-scale ramifications of introducing new technologies. And sometimes we don't see it ahead of time. These are emergent behaviors that come from the use of technologies that we may not have seen before. So what can we do? I think there need to be safeguards from the perspective of technologists who also interact with ethicists at a level where we can develop policies and understanding in terms of building some safeguards from the perspective of how it affects different levels of society, from, you know, individuals to smaller scale societies to the global level. And it's something that's very hard for technologists to do because we're not trained from that manner. We think of the new gadget that we're building or how efficient we can do something without thinking of the consequences. So I think it's a very important thing. But coming to what Victor was saying, I think interacting with our colleagues and others who understand what the ramifications are become very important.
Yeah, maybe I can add here. I would like to comment simply just one point, which I think is very important, the ethical part that you say, but again, it's going beyond technology. So it's very often a matter of how society evolves. So actually, one of the main points that I would like to raise is going back to what Manfred said. Oh, now everybody has phones, everybody is tracking information about where we are or we are not. You say that 10 years ago or 15 years ago, that would be a sacrilege for almost any country. Today, this is something that has become almost kind of acceptable from the general purpose perspective. And actually from the idea, for example, you have one of these tracking devices to see your healthcare and so on, and the status is even appreciated by many people. So now we had a discussion about vaccination. So I think these are elements that will also come into the perspective of this new technology. So I think it's important to really keep in mind all the angles for the evolution of whatever is societally acceptable from the ethical perspective, but we also have to bring in what are the benefits of doing all these things with these new technologies and see how not just the politicians, but really the public in general reacts. And based on that, we will actually need to come up with the different regulations and so on. For example, there was a recent discussion at the European Commission to come up with regulations about AI and deep learning methodologies. Well, the main conclusion was that we can regulate some things, but it's very difficult to see because things that right now are not acceptable in 10 years from now will be acceptable and vice versa. So it's very difficult to create guidelines that will always help, and we'll do that. Depends on how much benefit we get. So, and I think there is one of the important aspects is that it will not be a problem for us. Going back, I'm not throwing the stone to you again, Graziano, but it's not a problem for the technologies. We provide the technology to see what is feasible. And then we need to come up with the rest of the people doing the discussions of the policies about these ethical rules and so on, to see how these benefits may be translated in a way that is acceptable for society today and tomorrow, depending on what they have. But I think that we are not preventing any technology.
Yeah, but when you invent something new, you can use it in the good way and also in the bad way.
But this happens everywhere, right? So even drones today is already being used in many different ways. And
Exactly.
I don't want to mention the bad ones, but there are many different ways of doing that. Luckily, there was a recent study how to save dogs in the problem that they have in Spain with the volcanoes, how to use the drones not to put the risk members from the fire department, and just simply send a drone that will be able to catch the dog like this out of the blue in the middle of the fire. This is a positive way. There are many other negative ones. So I don't want to enter, but I think there is equal opportunities in both directions.
Perhaps I can make a comment what David said with the applications in medical area that is gaining more and more importance. Also because you can buy some electronic gadget and it is supervising your health state, your sleeping activities, and that is really working in a wonderful way. That's no question, and there are really certainly more serious applications where you have to cooperate with a medical doctor. And what I see is that in many universities of applied science in Germany, the classical communication area where students come and learn about communication, 3G, 4G and so on, these faculties run out of students, and the students now everywhere go for medical technologies. That's really an interesting thing to observe, and I think the professors in these domains, they must pay attention that they don't lose all their clientele from students. And concerning going to very modern technologies, I remember a talk of Professor Linville many years ago on these famous ISSCC conferences, and they were discussing what happens when we come to the limitations of silicon technology. And he said, don't worry, when you look to civil engineering, where they build bridges, houses with concrete material, they are certainly also at the limits of their technology, but still they are using that technology to go on and build further highway bridges and so on. So when we are coming to a certain limitation of silicon technology, and it looks like that, we still can operate, and the best example is that in the new factory of Bosch in Dresden, they say we start with 130 nanometer technology. That is the usual technology that is used in automotive applications at the moment. So it's quite a practical idea, and this open source hardware idea coupled with open source software is certainly also an interesting topic. Of course, we mentioned today very interesting topics like the design automation for quantum computing. That is really very interesting. But when I see the students, the typical student we have in our faculties, they have to work hard to understand quantum computing in general and working on these technologies. And I see it from our faculties in material science that are now some 20, 30 years old. At the beginning, they had excellent students. In the meantime, they have to fight for every student coming to work with them for a master or a PhD. And we must be careful that this does not happen in at least in electronic faculties. With computer science, you also will not be happy with every student coming to learn about machine learning and topics like that.
Okay, thank you, Manfred. I think that we finish our time. So I'd like to thank all of you for the interesting discussion. And I invite everyone to join the workshop for François Anceau next January. Thank you and have a good day.
Thank you.
It was a pleasure.
Thank you.
Bye-bye.
Thank you. Bye-bye. Thank you.
Bye-bye.
Bye.
Take care. Bye.